Okay, picking up where we left off. Where are we? We did parts A, B, and C. We thought about what it's like to revolve about the x-axis and then even tried out the y-axis. Okay, part D, what's happening here? And then part E, we're going to get some new things coming at us. All right, in part D, all we're told, y equals 4x, y equals x cubed about the x-axis. So first thing we want to do is start by graphing those. You may want to do this in Desmos. I'm just going to go ahead and give you the graph on paper here. Y equals 4x, we saw that before. Passes through the origin, something like this. Y equals x cubed. Y equals x cubed is going to do something kind of like this. It's going to pass through our line, both in quadrant 1 and in quadrant 3. And they're going to cross each other, actually 3 times if you count the origin, like so. What does that mean for the region? Well, there's going to be 2 regions, one here and one here. There are these pretty thin little zones. They're actually symmetrical. Here's what we're going to do. Oh, and then it's revolved about the x-axis like that. Okay, so what would happen here, right? Kind of as one spins down this way, the other spins up above, and it creates this kind of interesting shape. You notice though, if we were to only take half of it and spin around, it's the same volume for the other half. So why don't we take advantage of symmetry? We'll only find the volume here in the first quadrant, and then we can double it. Find the volume from Q1 and double. Okay, so let me draw just that part again. Make it a little bit easier for us. Here's y equals 4x, something like that. And x cubed, something like this. And here's our region. Okay. So let's think about this, and it's revolved about the x-axis. Okay. Is this a disk or a washer? Well, as that revolves, yeah, it comes down to the origin there, but there's that big gap everywhere else. That is a washer for sure. And so let's draw the outer radius and inner radius. The outer radius goes all the way to the outer edge. The inner radius goes to the inner edge of the region, like so. So let's see, what does capital R of x equal? Well, the outer edge, that's that outer line, it's 4x. This is in terms of x because it's around the x-axis. How about little r of x? That's going to be x cubed, that inner function there. And now we definitely need to know the limits of integration. They cross here at 0, but where do they cross here? You might get that from a graph. You might be able to clearly see, or maybe you can figure it out just by looking at the functions. Where would those be equal? And it turns out it's at 2. Right? 2 cubed is the same as 4 times 2. Okay. Very nice. And remember we got to double this whole thing. Okay, so for the volume, it's going to be 2 pi, since we're doubling, from 0 to 2. And then we'll take 4x squared minus x cubed squared dx. Outer radius squared minus inner radius squared. Okay, if you made it this far, then we're probably home free. 16x squared minus x to the 6th. This is going to be 16 over 3x cubed minus 1/7 x to the 7th, 0 to 2. And then plugging in, let's see, 16 over 3 times 2 cubed minus 1/7 times 2 to the 7th minus, and then plugging in 0 again, 0. Be careful with that. People can get complacent with zeros and they think it's always going to be 0 when you plug it. Well, it is for a polynomial, not for trig and that sort of thing necessarily. All right, what do we got here? Let's knock out the final answer. We got 16 over 3 times 2 to the 3rd minus 1/7 times 2 to the 7th. What could this be? Oh, and then we got to multiply by 2 pi. So let's multiply by 2. I got 1024 pi over 21. There we go. Okay, very nice. But again, what was helpful, right? Noticing the symmetry was really helpful. If we had not noticed the symmetry, then we would have had to do 2 separate integrals anyway, because you notice, well, is that true? No, because even down here, the outer radius, I was thinking top bottom, but that's not how we do this. The outer radius would have still been 4x. And the inner radius would have still been x cubed, even for negative numbers. But even that said, noticing the symmetry, I think, simplified things a lot. We could just focus right there, redraw it, draw the outer, draw the inner, identify those quickly, and yeah, good to go. Okay, we got one more example. This one, we revolve about a different line other than the x or y axis. So we got y equals x cubed, y equals 8, x equals 0, about x equals 2. The line, the vertical line, x equals 2. All right, let's draw this thing. Going to draw it kind of big, x cubed coming down like this. Okay, y equals 8, this horizontal line. Okay, x equals 0 right here. So we've got this region. Looks good. But now we're rotating around x equals 2. Now this is key to being careful with your graph. Turns out where those intersect, that's right at 2. And that's something we need to notice, that x equals 2 is right there, right? If we put it too far or put it in, that's going to throw us off. There it is. And we're rotating, maybe I'll say like that. So this region spinning around that way. Okay. So what do we notice here? Maybe first thing, is this a disc or a washer? Well, it's a washer, because we'll have that big gap here as that thing spins around. There'll be that big hole in the middle. Okay, what else? How are we going to integrate? Notice we've got a vertical line. So we're going to integrate with respect to y, or you might even just note use dy. Maybe that's That's kind of makes it clear, right? Okay, if we're going to use dy, then a couple things. We need to rewrite any functions in terms of x. Let's see, y equals x cubed would be x equals cube root of y, or maybe we say y to the 1/3. Let's do that. That's it. What are the limits on y vertically? Starting at 0, going up to 8. Not too bad this time. All right. And now finally, let's draw the outer radius, inner radius. So you begin on the axis, and then you come out perpendicular. There's the outer radius. Here's the inner radius. Okay. What gets tricky when you're not revolving about in one of the either the x-axis or y-axis are getting your radii, outer radii, inner radii, or whatever you need. That's what you got to be careful with. Okay, let's see here. So outer radius, capital R of y. That's actually not bad. It's always that full length across. That's 8 units. Is that 8? No, whoa, I got to slow down. 8 is up here. How many units across is this? It's 2. My mistake. It's always exactly 2 units the whole way. Okay. How about R of y? Now this one is changing and you're not on an axis. Okay, so let's think here. We just want this little distance here. How are we going to get it? Well, we know the entire thing, right, is 2. And can we figure out the distance just here across the region? Could we figure this out? If we know the whole thing is 2 and we can figure out this portion, then if we subtract them, we can get what's left. What is that? So, and we're kind of like, we're taking advantage of starting from an axis and then going out to the function. So starting on the y-axis and moving out to the function, isn't that this y cubed, or excuse me, cube root y to the 1/3 is that distance here. And the whole thing is 2, so R of y is 2 minus y to the 1/3. Oh yeah, that's how we'll do it. Now, if you wanted to check yourself, you could, right? You could say, hey, what do I see as the radius when y equals 0? Well, when y equals 0, it's 2, right? The full thing. Well, if I plug in y equals 0, yep, I do get a radius of 2. And what's the radius at the very top when y equals 8? Well, that radius I can see is 0. Well, if I plug in 8, does it really give me 0? Sure does. 8 to the 1/3 is 2, 2 minus 2, and it all checks out. Okay, once we have that, we can set it up. Pi integral from 0 to 8, 2 squared minus 2 minus y to the 1/3 squared dy. And it's going to take a little bit of work, but no problem. That's 4 minus, let's see, maybe I'll keep parentheses here. Foiling this would be 4 minus 4y to the 1/3 plus y to the 2/3 dy. Simplifying, 4 minus 4 gone. That's going to be 4y to the 1/3 minus y to the 2/3. Looking good. Pi. Okay, I think we're ready. Let's see, what are we going to have here? Y to the 4/3. What would that be? 3? We cancel out and get a 4. minus, that'd be 5/3, so 3/5 y to the 5/3 from 0 to 8. Okay, we're almost there. Plugging in pi. Let's see, 3 times 8 to the 4/3. I think that's all going to come out nicely. 5/3. Plugging in 0 is 0. Okay. Let's get our final answer. 3 times 8 to the 4/3 minus 3/5 times 8 to the 5/3 is 144 over 5, 144 pi over 5. Got it. All right, so these last calculations, I mean, it is what it is. We need to do that, but right, it's all about that setup. And these are tricky, right? I mean, this is about as tough as they get when you're not revolving about an axis with a washer. So, you know, again, we'll use that trick. We'll still measure off the axis, but then know that it's that total distance minus this. Came in really handy there. All right, everybody. Hey, that's the end of this section. Check out the homework.